Okay, so this is a screencast to kick us off for Chapter 2. I'm going to cover a little bit of history of atomic theory, look at the structure of the atom in the periodic table, kind of introduced to that, and also look at isotopes and some introductory stuff as a precursor to nomenclature. So, looking at sort of the beginning of this unit, we're getting some background information on the atom. As we know, chemistry is pretty much how matter interacts, and matter is made of atoms. So we start sort of with the models of the atom. The one that seems to be most familiar to most people is this idea of the atom as being some sort of circular thing. Prior to us knowing anything about what was in it, we had Democritus, who treated the atom like what we sometimes call the billiard ball model. Okay, and the billiard ball being the idea that it was a solid sphere and each kind of element had its own sphere, right? It was unbreakable, small, indivisible particles. Following that, we get, a little bit later on, we start discovering the parts of the atom, and you see things like the Rutherford's golden foil experiment, where he fired alpha particles at a sheet of gold. The result that he expected, based on prior models, which I guess I should do first, J.J. Thomson, or the plum pudding model, they expected sort of positive stuff with little negative charges because that electron had been discovered prior to that by J.J. Thomson. So we have the plum pudding model and the idea that these negative things would be stuck into a positive substance. Rutherford comes along and they decide to just start shooting some alpha particles at the gold foil. And they expect that because these alpha particles, as they expect them to be, are quite big, that they should go right through or maybe deflect a little bit, depending on how much, how fast they were going. What they actually get, the actual result, is that some of them bounced straight back. And what that suggested is that the atom somehow has a large positive center, which they call the nucleus, with the negative charges circling around. So we end up with what's called the Bohr model of the atom. The Bohr model gives us this idea of electrons at different energies around a central nucleus. In the nucleus of an atom, we have protons, which are positively charged, and we have neutrons, which are neutral in charge. And those are held together by the nuclear forces, and that keeps the atom together. The identity of an atom, or the name of that element, is based on the number of protons that element has. Okay? So we have various sort of charges and masses of protons, neutrons, and electrons. Those would be things that would be given to you, so I'm not going to actually make you memorize those or cover them here. But note that the electron is much, much less massive than a proton. So if we consider a proton, let's look at relative mass. A proton and a neutron have the same relative mass, which we give it this U, this idea of the atomic unit. The electron has a relative mass of 1/1836 U, so it's much, much smaller. However, the proton has a charge of +1, the neutron has a 0 charge, and the electron has a -1 charge. So we can look at those. As we start to talk about these atoms, we're going to look at ways of communicating. So we have what's called a notation. So for example, let's look at helium. Okay, going back, we have two numbers that we report. We have Z, which is the atomic number, usually printed above the symbol on like this, and then you have A, that is the mass number. And that usually doesn't always appear on the periodic table, but they might, based on the periodic table you're looking at. Usually, what appears below is the average atomic mass of all the isotopes of something. So what you need to know about the periodic table and these numbers is that the atomic number tells us the number of protons in the nucleus, and the mass number tells us the number of protons plus the number of neutrons. And when something has a consistent number of protons but different number of neutrons, that's called an isotope. So the number of neutrons is different when we have an isotope. Okay, so on the periodic table, things are organized. You have periods going this way, and then you have groups or families going this way. We're just going to call them groups for now because they are group numbered 1 through 18, or group 1A, 2A, 3A, etc. on the periodic table. And so you'll need to know that those groups exist, and the fact that when we look at the periodic table, we kind of look at it like this. Over here, we have the nonmetals, and then we have metals over here. And the metals are broken up into different groups. You might have the alkali earth metals, you could have the transition metals, you could have the metalloids. So these are all group names that you can be familiar with from your reading. All right, so back to isotopes. The idea that atoms have different numbers of neutrons leads to a modification to Dalton's original atomic theory. So the original atomic theory, which you should have read about, says that first, elements are made from atoms. That's his first part of his theory. The second part says that all atoms of an element are the same. And that's the one where this gets tricky because of the idea of isotopes. The third is that atoms of one element are different than atoms of another. Meaning that something like hydrogen atoms are different than carbon atoms. They're not just like special variations on each other. The fourth is that atoms combine to form compounds. And from this atoms combine to form compounds thing, we get the law of definite proportions, which we've talked about extensively in class. And then the fifth one is that atoms cannot be created or destroyed in a chemical reaction. So atoms are not created, nor are they destroyed. They are merely rearranged in a chemical reaction. Okay, so what that leads us to is this idea of isotopes, and that makes us have to modify this all elements of our atoms of an element are the same. They are not all identical, okay? So what is the same, however, is that all atoms, so this is the modification to rule number 2 of that theory, all atoms of the same element have the same number of protons, and if they're neutral atoms, electrons, but can have different numbers of neutrons. Okay, so that's the modification to Dalton's atomic theory, and that comes from the idea of isotopes. And since it's the electrons that affect the chemical properties, isotopes all have the same properties. So something you may not know is that electrons, an electron configuration, and electron arrangement determines the chemical properties of a substance. So the fact that all atoms of the same element have the same number of protons and electrons means that having different numbers of neutrons does not affect the chemical properties. So isotopes, which are those with different numbers of neutrons, all have the same chemical properties. Okay, so an example of an isotope might be neon. The element neon has 3 isotopes. There's neon 22, neon 20, and neon 21. And all of those isotopes have different abundances. Abundance tells us what percentage of a collection of neon will be that isotope. Isotope neon-22 has an abundance of 8%. Neon-20 has an abundance of 90%, and neon-21 has an abundance of 2%. So we would expect that the atomic mass of neon, because that is a weighted average, will be closer to 90%. But how do we find that out? So atomic mass is what we call a weighted average. Okay, so let's take that. Let's say if 90% has to have a mass number of 20, plus 8%, which is 0.08, is 22, plus 0.02 is 21. When we do that math, which I'm going to do right here, we take 0.9 times 20 plus 0.08 times 22 plus 0.02 times 21. We get an average atomic mass of 20.18. So we can see that it's very close to 20. We would expect that because that one has a greater weight. It's worth more in the atomic mass calculation. When we look at the periodic table, you find that, in fact, neon has an atomic mass, which is the number written under the symbol, very close to 20.18. Okay, so if you wanted to do an example problem of that, here's one that you can try, and you can ask me about it in class, and I'll give you the answer. But let's say we have rubidium, okay? Rubidium has rubidium 85, and then there's also rubidium 87, and the percent abundance for this, the 85 is 72% abundant, and the other is 28%. So go ahead and see if you can calculate the average atomic mass of rubidium, and I'll give the answer in class. Finally, sort of in this introductory chapter, we are going to talk about molecules and ions, because we are going to be getting into nomenclature next, naming things. So a couple of vocab terms. First, molecule. All right, a molecule is a definite arrangement of atoms joined by a chemical bond. And remember, by the law of definite proportions, that's always a fixed proportion. So molecules can be elements or they can be compounds. Okay, so elements can make up a molecule, and then compounds are referred to as molecules. One unit of a compound is referred to as a molecule. They're usually formed between two nonmetals. Okay, molecules are usually two nonmetals. So some examples of molecules, you have H2, O2, N2, F2, Cl2, and I2. These are called the diatomic elements. When they're in nature, they're not alone. They're usually bonded to another of their own atoms. So they're called the diatomic elements. They are a compound, or they are a molecule, but not necessarily a compound, because the definition of element is all the same type of atom. There are also molecules, one that you're very familiar with, water. That's a compound, because it's more than one type of element, and it's called a polyatomic molecule. Okay. Third kind of molecule, third example might be something like ammonia, which we've talked about, which is a polyatomic molecule. Notice that hydrogen and oxygen are both nonmetals. Nitrogen and hydrogen, both nonmetals. And that's a compound rather than an element. So all these things are things we would refer to as molecules or molecular substances. On the other side of that, we have ions. Okay? Ions have either excess or lacking electrons. For example, sodium, atomic symbol Na, when we look at it on the periodic table, sodium, when it's neutral sodium atom, which by the way does not happen very often, it is 11. Okay, so it has an 11 up here. That means when it's a neutral atom, it has usually 11 protons and 11 electrons. We don't worry about the neutrons right now. If we bring sodium into the area of another element, like chlorine, for example, sodium has a tendency to lose an electron. So what we end up with is what is called sodium ion, which still has 11 protons, but it's lost an electron. So when you look at it, the overall charge when it's neutral is 0. The overall charge here is a positive 1, so we call this sodium ion. A positive ion, here's where I get to bring in my cat joke. Cat ions are positive, okay? Cations are positive. Hooray for cat jokes. Positive ions are called cations. The other way to remember the difference between cation and anion is that cation has a positive sign right in the middle of the word. So that's a cation, positive ion. That's when something has less than its neutral amount of electrons. When something has more than its neutral amount, like I said, chlorine is number, let me guess here and say 17. I don't have it memorized. It's number 17. Chlorine is 17. When chlorine is neutral, it has 17 protons, 17 electrons. But it very often will take on an excess electron, and we'll talk about why that is in more detail. Some of you might remember from your first chemistry course. But when we have chloride ion, we have 17 protons and 18 electrons, and that's called chloride ion. And it is called an anion because it is negatively charged. Right, and 17 minus 17 is 0. 17 plus, you compare the difference between 17 and 17, that's 0. This is a -1 difference, so it's called an anion, negatively charged. All right, so there are these ions, when you take an element and give it an extra electron or take them away, are called monatomic elements. They're just elements of ions of elements. However, we also have what are called polyatomic ions, and I'll give you a list in class of what those are and what you need to know. One example of that might be this ion here, which is called carbonate ion. And I'll go over the polyatomic ions and how you need to know, what you need to know about them, their charge, their name, etc. in class. The next step for us is going to be nomenclature. We're going to learn how to name things.